Okay, let's get started. So it's the last lecture for 16A. Congratulations, you all made it. You survived. Good job. It's been a good semester. Thank you, everyone. And a big, big thanks to all of the TAs and ASCs because, you know, this would not be possible without the tremendous amount of work that every single person on the TA staff, every single ASC, every single lab assistant, every single person who helped in office hours, every single person in the EECS department staff who painstakingly printed out 1,100 exams so every one of you could take the exam. The fabulous people at ETS who make sure that the webcasts are up and running for us. They've all been working super hard, and this would not work at this scale without any of them. Of course, it hasn't been perfect. There's been ups and downs. Stuff has gone wrong in places, but thanks to everyone, and thanks for everything that, you've been doing to make this good, and thanks to all of the TAs and all of the ASCs and all of the staff who've been working really hard also to make this a possibility. So with that, we're going to kind of try and wrap up the entire semester today. And today's class is going to be basically going back to the very beginning of class and talking about what we talked about in Module 1 again, but also pointing a little bit towards the future and giving you a hint of what is to come in the rest of your classes that you will be taking in the department. So this meme is actually a meme that was made by one of the previous semesters, and I think it's just a great reminder of Module 1. I think it's actually quite funny. It took a minute for me to get it when I first saw it, but it's one of the ones that I really like, so I thought it would be fun to share, especially because what I really want to start off talking about in today's lecture is OMP for imaging. So could I switch to the doc cams, please? Thank you. So last time we've talked about this OMP algorithm, right? And what this OMP algorithm is talking about is it's saying, well, you have a received signal. There's a bunch of candidate signals that are transmitting, and you don't know which of them are transmitting and which ones aren't. There's, millions of, say, candidate signals, but only a handful, say, 5 or 10 of them are actually transmitting. And you want to figure out how to identify which devices are transmitting, even though you have far more unknowns than you actually have equations. That's the OMP setup that we actually talked about. And what is the OMP algorithm? So let me... Can people read this? Yes? No? Bigger? Okay. So what are we saying? The OMP algorithm says, well, first, what is our list of signals that we know are present? It's empty. S represents the list of signals that we know are present. This is empty because when we start, we don't know who's present, who isn't. And what is the unexplained part of our signal, right? The unexplained part of our signal is basically the entire signal, right? Because we haven't identified any signatures that we know are present for sure. So our unexplained part, or this error vector E, is the entire received signal. And the list of signatures that are present is basically the empty matrix. Then what do? You say, well, let me take, the unexplained part. In the first iteration, the unexplained part is basically the entire received signal. And look at the inner products, or the cross correlations. Remember, it's important to note that inner products and cross correlations are not different things, really, right? Cross correlations are just a series of shifted inner products. So I got some questions about why cross correlation, why inner products. The reason we use these terminologies interchangeably is that cross-correlation is just inner products of shifted signals. So this terminology basically means the same thing. Don't worry about using either one. Inner product means that you have no shift between them. Cross-correlation means that your signals are potentially shifting. So here, in this case, when we don't really have to worry about any time delays, what we're going to do is we're going to say, let's take an inner product with every single's candidate signature, and I find that signature that produces the largest inner product. This word argmax is short form for the maximizing argument. Argument here is basically these SIs. These SIs are changing. So what this notation means is it says, find that signature that maximizes this inner product. Let's call that S-max. After this, you say, well, we declare that S-max is present. So we add this S-max to our list of potential devices, right? We say that S-max is now a device that is present, and we basically update our list. The first time we're doing this matrix is just going to be a column, right? Because there is no, it was initially empty, there was no signature, so the first signature is a column. The second iteration, you will have a matrix with 2 columns. The third iteration, you will have a matrix with 3 columns, so on and so forth. Right? Once you have this matrix, then you say, well, how do these signatures together, if it's the first iteration, you just have 1 signature. If it's the second iteration, you have 2 signatures. How do these collectively explain what the, unexplained signal is doing? How does it collectively explain the received signal, right? So you say project R onto the columns of S, right? Notice we're not saying project E. We're saying project R, which is the entire received signal, onto the columns of S, because basically this is saying, using the linear combinations of the columns of S, how close can you get to R? So you do that, and then you say, well, let me get that projection. Let me remove it from R, and that gives me my remaining unexplained portion. Right? Once you have this, you've done the best you can do explaining with the signals you've picked out so far. Go back and pick out the next loudest signal. Okay? And you asked many good questions about how and when to stop, and we had some, answers for this. We said, well, you can say that if I know the number of devices that are going to be talking, say I know that there's 10 devices that are talking, after I do this 10 times, I stop. Or I can look at the magnitude of this error vector E, and after that magnitude gets super small, it's so small that it could only really be some kind of interference or noise, then I say, okay, I'm going to stop. At the end of lecture today, we're going to talk about validation, and this will give you another way of trying to figure out how to potentially stop this OMP algorithm. So today, we are going to get to OMP for imaging and validation. These are the two ideas that I want to get across. So going back to module 1, where we talked a lot about imaging, right? You did imaging of fairly large images, right? So let's say you were trying to image a very large image. Say you had an image that is 100 by 100 pixels. Okay? In module 1, to be able to, image a 100 by 100 image, to be able to take a picture of it, to be able to recreate it, how many measurements did you need to take? Anyone remembers? If you had 10 to the 4 pixels in your image, how many measurements were needed? 10 to the 4, right? That's what you did in the first lab of the class. Now that we have more advanced techniques at our disposal, can there possibly be a way that we could do it in fewer measurements? And, be able to reconstruct the image even though we have, let's say, less data. So in module 1, this required 10 to the 4 measurements. Can we do with less? That's what we really want to try and figure out. And at some level, if we wanted to recover every single pixel exactly with absolutely no noise, is it possible to do it with less than 10 to the 4 measurements? No, for a general image, there's actually nothing we can do. But what if we had some side information? What if we knew our image is sparse? What do I mean again by sparse? I mean that most of the pixels are black. When you represent that numerically, it means that the pixel is basically the pixel number is a 0. And there's some smaller number of, non-zero pixels. If you have this structure, then suddenly we're in a setup which seems a lot like the OMP setup, right? Where we had one received signal, there's few things that are transmitting, and the other ones are really quiet. So most of the alphas are 0. In this case here, most of the alphas are 0. Some of them are non-zero, right? And that the number that is non-zero is far smaller than the number that is actually 0. So let's try and see how we can replicate this in this imaging setup. So let me represent our image as a vector, just like you did in the module 1 labs. Let's say there is x 10,000, some large number of pixels, right? And now we want to see what we can do with, say, a smaller number of measurements. So I don't really want to do out an example that has 10,000 variables, because then the entire lecture will go away in just writing it out. So I'm going to do a smaller example, but hopefully you'll get the gist of what I'm trying to say. So let's say we have the following setup, where I have x1, x2, x3, x4, x5, x6, x7, x8, x9, x10. This is my image. And I want to take, some number of measurements of it. Let's say I want to take 4 measurements. So I'm going to write this as 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, and 0, 1, 1, 0. Okay? So there's a structure to these measurements, if you can see, right? First, these first 4 columns only have 1 1 in them, and then the remaining 6 all have 2 1s in them. Right? But how many measurements does this matrix imply? How many measurements am I taking? How many columns are there and how many rows are there? There's 4 rows and 10 columns, right? So there's 10 unknowns. That's why there's 10 columns. So I have columns C1, C2, C10, and I have 4 rows, so I have 4 measurements. And let's say I take this mask, and just like you did in module 1, I shine this mask onto this image, and I get back a received vector. and I get back this vector, let's say 1, 2, 0, 1. Right? So now I have 4 equations and 10 unknowns. Right? This is not going to be solvable using our typical module 1 solutions. But what if I told you only 2 of the 10 pixels are non-zero? Most of them are actually going to be 0. Only 2 of them are non-zero. How can we go about, trying to understand this, solve this? Can we somehow use the OMP algorithm to, follow the same strategy? Every pixel is now playing the role of a device, and every column is basically corresponding to the contribution of a pixel in the received vector. Right? So take a minute, think about it, think about how this might be connected to OMP, and see if there's a parallel here that you think is worth exploring. Feel free to talk to your neighbors. Just try and understand the setup here. Okay, so does everyone kind of see how this is parallel? Are there any questions about how this might actually parallel the OMP setup with the, few devices transmitting and a received signal? Yes?
So in the Omp algorithm, we had a matrix full of gold codes, and we knew what the gold codes were that were present in our received signal. But when
We didn't know which gold codes were present, right? We didn't know which devices were transmitting.
But we knew the gold codes for each device.
We knew the gold codes for each device.
But in this case, when we're doing imaging, you don't necessarily know what the pixels of each different image.
Yeah, the great point is you don't know what each pixel, like the pixels aren't transmitting anything, right? It's not like there's a code associated with every pixel. So it's a slightly different setup in that sense. You're exactly right. So can we somehow parallel it nonetheless? Excellent observation. Yeah?
I have a question on the R1 vector. So when we do the error vector, do we do R minus R or do we do R minus S times R1?
You're right. We actually do R minus S times R1. You're right. Thank you. Type 1, my part. Yes, question. Yeah, the question is, how is the mask basically, like the gold codes have this property of being orthogonal to each other. They have all these nice structures, and where is this structure here? So all these are great questions, and it's right, it's not exactly a parallel. However, let's try and look at this, right? So when I have a matrix times a vector, I know this matrix times this vector is equal to this other vector, which is very similar to this setup here, right? So here, every column represents a signature. Instead of having every column here be a gold code, what we have here is every column basically represents this pixel's contribution to this received vector. Right? Because when I write this entire thing out, what is this matrix vector multiplication? This is C1 times X1 plus C2 times X2 plus C3 times X3 is equal to this received vector Y, right? Or let's call this received vector R. And I have basically so C1 X1 plus C2 X2 plus C3 X3 plus C10 X10 is equal to R, right? So here, if you compare these two, the X's are exactly like the alphas, and the C's are exactly like the S's. Does everyone see this? So you can think about every column here as basically the signature of that pixel. If that pixel was on, then this signature would be present in your received signal. If that pixel is off, if that's a 0, then this signature is not going to be present in your received signal. Does everyone see how the two problems are essentially equivalent? Of course, you don't want to set up a matrix where basically all of these columns are linearly dependent or exactly the same, because then you're not going to be able to identify the different columns through our inner product strategy, right? So there is some level of structure that you want to take in the measurement. However, we can actually go ahead and run the OMP algorithm even though there's far less than 10 measurements that are being taken here. Does everyone see the parallel? Okay, so let's actually try and follow through with this. So why don't you start taking inner products of every single column with this received vector R? So we'll follow our first step of the algorithm is take inner products. And we can do it quickly together because these columns are so easy. If you take the inner product of the first column with this R, you're just going to get 1. The second column and this is just going to give you 2. The third column is going to give you 0. The fourth column is going to give you 1. Fifth column gives you 3. Sixth column gives you 1. The seventh column gives you 3. Eighth column gives you 1. This gives you 2. And this gives you 2. Right? So what we saw was that inner product of R and C5, C3, C4, C5, C6, C7, C8, C9. This is equal to 3. An inner product of R and C7 is also equal to 3. Right? And these are the two largest inner products. I don't want to spend time doing out every single inner product, but if you couldn't follow along my quick inner product calculations, go and practice this. It's good practice to be, have fluency with inner products. But now we have two different signatures, right? The columns are just like the signatures. We have two signatures that have the exact same impact. How do we, what do? We can just choose any one. If they're exactly the same, this will never happen in a real scenario. This is just because I'm rigging this to make an easy class demo. But it doesn't matter. Just pick either one and continue on. So let's say C5 is present. So saying C5 is present is essentially saying that X5 is non-zero. Right? Because you have a C5 X5 that is giving me my received vector R. So now I'm going to project R onto C5. And I'm going to get my x5 hat to be basically C5 transpose C5 inverse C5 transpose times R. Right? What are we doing? We're saying C5 is present. Let us use C5 to explain R. Right? All I'm doing is this projection step of our algorithm. This step right here. Okay? So now we have this is equal to 1, 1, 0, 0, 1, 1, 0, 0, inverse 1, 1, 0, 0, 1, 2, 0, 1. Right? Because C5 is just equal to 1, 1, 0, 0. What is C5 transpose times C5? Or just take a minute to solve this out. Tell me what you get. Yes, question at the back? You have to speak up. This is just the coefficient. So we're going to subtract x5 hat times c5 from the received signal. This is just the coefficient. Yes? No, that would not be a good idea. Yes? Why is the length of the vector 4? Because we took 4 measurements. We just, we decided to take 4 measurements. We wanted to see if we could do it in 4 measurements. If we took 5 measurements, it would be 5. If we took 3 measurements, it would be 3. For the first iteration, can we just use the projection formula? Absolutely. This is exactly equal to the projection formula. Question at the back. A single measurement is just exactly what you did in the first lab, right? This row times this column gives me 1. So this is basically all of the pixels in the image. This is the light. Like basically, remember when you did module 1 imaging, you basically had these masks, right? Where there was dark some places and 1 some places. So this is exactly this. So this is basically saying that I'm going to take a measurement that shines light on pixel 1, 5, 8, and 9. Right? And everywhere else I'm going to put black. That's the first mask. The second mask has pixel 2 and pixel 5 and so on. Does that make sense? Yes. Why did I choose C5? Because it had the largest inner product with R. Because you can choose arbitrarily. It doesn't matter. If you have 2 equal things, it doesn't matter.
Is the projection of R onto C5 equal to X5 or like C5, X5? What's the difference?
The projection, when you, this is equal to x5 hat. This formula is basically the coefficient that gives you x5 hat. If you now wanted to figure out this projection onto C5, you would have to multiply it by a C5. Yeah. Okay, so this is 1.5, right? This is, what we get out from this is always a scalar, right? This cannot be a vector, right? The dimensions don't allow it to be a vector. So to get a vector out of this, I cannot subtract just x5 from R. I have to subtract basically x5 times c5, because x5 is the component of c5 that is present in R. Does that make sense? Okay. Okay. Everyone with me here? Good? Okay. Good. Now we're going to remove 1.5 times c5 from R, right? So R1 is equal to R minus 1.5 times 1100. What is R? 1201 minus 1.5, 1.50, 0, which gives me basically minus 0.5, 0.501. Okay? Okay, so now we have this. So now we're going to say, let's consider the next step. Inner product of R1 with C1, inner product of R1 with C2, so on and so forth. R1 with C10. Right? We're going to do this inner product. So here, I guess I changed my notation a little bit. This is exactly equal to E. Because this notation is a little bit different from what I'm using here. Let's call this maybe, let me call this alpha hat. Okay, sorry. I'm not going to try and fix this notation. I will fix this and post a corrected notation one on the website. Don't worry about this notation. Just follow what I'm doing right here. So what did we do? We have this R. We have this received vector. We say that C5 is a component, right? C5 is a component. And so now I'm going to subtract from R the part of R that can be explained by C5. Okay, does everyone understand what we've done here so far? Okay. Now, whatever this remainder is, which I'm going to call R1 or E, I'm going to consider all these inner products. Okay? Once we have all of these inner products, which one is the maximum? If I take minus 0.5, 0.501, and I inner product it with every single one of these. C7 has the maximum inner product, right? It so turned out that earlier also we had C7, but doesn't matter. That was just luck. What matters is that now again C7 has the maximum inner product. Okay, so now that we know that C7 has the maximum inner product, what are we going to do to our S matrix? Our S matrix initially here, we just had this C5, so it was just C5. Now our S matrix is basically C5, C7, because we now have both of these as identified, right? So what does this mean? If I have C5 and C7, that means I have pixel X5 and X7 turned on, right? So I'm saying to explain my observations when I took this measurement, I'm going to say, well, x5 and x7 were non-zero, everything else was 0. Now what do I do next? Now I say, well, explain R using both C5 and C7. Okay? So now S is equal to C5, C7 is equal to 1, 1, 0, 0, 0, 1, 0, 1. Now I want to project my received vector R onto S. Okay? And how am I going to do this? I'm going to use basically the least squares formula, and so I'm going to get my x5, x7 is equal to S transpose S inverse S transpose times R. Right? These are the two things that I'm projecting onto. This is my received vector R. So what is this equal to? This is now equal to 1, 1, 0, 0, 0, 1, 0, 1. This is S transpose. S is equal to 1, 1, 0, 0, 0, 1, 0, 1. All of this inverse times 1, 1, 0, 0, 0, 1, 0, 1 times my received vector, which is 1, 2, 0, 1. Okay? Is everyone following me up to this point? Yes, question. This is, okay, so everyone please pay attention. I've had this question twice now. It's a good question, but make sure it doesn't, it's a cooked up example. It just happens that these are equal. You will, if you have two things that are equal, it doesn't matter. You can choose any one of them randomly. So if you have two inner products that are equal, you don't necessarily know that both of them are present. They might be phantoms that are still, you have no way of knowing. So you want to make sure that it shows up in the second round. You could have also done just C7. You would have started with C7. Because this is a cooked up example, you would have gotten C5 as the next one. And in this specific corner case, it would have worked. But in general, it will not. This is because this is a classroom example with 10 pixels and 4 measurements, which is never a real-world situation that you're actually going to end up in. So don't worry about the fact that these inner products are exactly equal. Okay? So we have basically these two. It doesn't matter that these happen to be equal. This is just pure fluke. Does that answer the question? Yeah? Okay, great. Yes? Why does the signal or image need to be sparse? Hold on to that, we'll get to that. But basically, the thing is that if the signal or image isn't sparse, then I cannot make this assumption that most of my pixels are zeros. The only reason this works is that I want to explain my R by turning on as few pixels as possible. Basically, at some point, my process will entirely break down if my signal isn't sparse. I will start to, read values that are not actually there. If my signal isn't sparse, I cannot get away from needing 10,000 measurements for 10,000 pixels. The structure that is in there that says that most of the things are zeros is what allows me to do this. Does that make sense? Yes?
When we did this process with like our satellites, we knew that the columns were near orthogonal, and that's why it didn't have a create as omnipresent. If these aren't near orthogonal, can we still make that guarantee when we do our OMP process?
If these are, good question. Like basically, you're saying that does there need to be some structure on these columns? And you basically do want to choose these columns to be near orthogonal. OMP will still work, like it's an algorithm, you can still execute it, but it'll work better, and you will basically know that you get the right answer if you have some kind of structure. So you don't want to have a bunch of columns that are linearly dependent here. That would make this fail. This would not work for any arbitrary columns. Like there's a structure to these columns, and there's that structure for a reason. Okay, so I'm not going to do this algebra out. You can do it when you get home. But this is basically, turns out to be equal to exactly 1, 1, right? You can verify it if you want. And now when you look at this received vector 1, 2, 0, 1, and you look at C5 and C7, right? What is R? It's just C5 plus C7, right? And so here, what this is saying is, what was the estimate that you got for X5 when you just projected onto C5? You got 1.5, right? But when you see now this better estimate using both the columns, you're actually doing a better job than if you had just used this estimate and not update it using the new information that you had gotten. Right? This is why you want to keep updating your estimates for the unknowns every time you discover a new device. Basically, if you keep the old estimates, that's old estimates with less information. The fact that you can now make a better estimate using all of the information you have will lead to better answers. That's why you want to keep doing this, and you don't want to just say that, okay, well, let me keep my estimate here, and let me now just estimate X7, instead of trying to estimate both of them together. We're going to do an example in discussion tomorrow that's going to talk more about exactly this point. So if you still have some questions about this, please make sure you attend discussion, sorry, not tomorrow, but Monday's discussion. Okay? So now that you've seen this OMP procedure out in an example, is everyone clear on what these steps are and what we're doing by saying, okay, well, let's explain it by the signatures we have, and then, remove them one by one. Question? The question was, if we had another pixel and we wanted to do this again, then S would indeed have a third column, and then you would get a 4x3 matrix, exactly. So here S was just a column, here it's 2 columns, then there'll be 3 columns, so on and so forth. And you can see that basically, right now, the error vector, or the residual you have when you put X5 and X7 is exactly 0, right? Because what do you have? X5, so this is X5 hat, X7 hat, X5 hat times C5 plus X7 hat times C7 is exactly equal to 1, 2, 0, 1, right? This is exactly equal to R, because this is 1 times 1, 1, 0, 0 plus 1 times 0, 1, 0, 1. Right? So here we've explained everything. The unexplained part is exactly 0. R minus this R1 is equal to 0. So in this case, we've actually explained all of R, now that we've found these two things. Other questions? Yes? What happens if our, the image isn't sparse? Basically, this will not work. This only works when you have sparse images. But let's try and do this now in an actual setup. So, Can I have one of the cameras connect to my laptop? Perfect. Thank you. So what we have here is basically 100 by 100 image. And instead of taking 10 to the 4 measurements, we want to take only 7,000. And we know the sparsity of the image. We know that the sparsity of the image is basically 960. And we're taking these measurements. So we have measurements, and the number of measurements we have is basically 7,000. So the column that we have is something like this. So all we're given is this. This basically parallels this received vector here. The measurements vector that I'm pointing to in the IPython notebook is the same as this R. And I also know this measurement matrix, right? So I've generated this measurement matrix. I know this received vector. And what I'm going to do is now basically run OMP on this. And let's see what actually happens. So the things to note from this, right? You don't have to read all of the code. What I want you to see is that this has 10,000 pixels. We are taking 7,000 measurements, right? All we're given is basically this vector. And we have this mask, right? This mask is known to us. This mask is basically generated by randomly putting zeros and ones. Random generated masks often give you columns that are very close to orthogonal, which is why they work. So we have this mask, we have these measurements, and now we're going to use OMP to actually recover this. So what this is saying is that the bottom is the iteration number of the OMP. So it's keep going, and every time it's choosing one pixel to light up. So as you can see, every new number, it's one extra pixel goes from black to white. Everything there is black right now because we're assuming that most of the pixels are 0. Okay? And as you'll see, it'll take quite a bit of time. While this is running, I'll take another question if there is one. Yes? Are we under the assumption that the values of x are between 0 and 1? We don't have to make that explicit assumption in OMP because this is working without that assumption, but because the values are between 0 and 1, the values that are being returned are also being 0 and 1 because it's actually picking out fairly correct values. Other questions? Yes?
So the example of the devices, the column comes in the code codes. Is there any significance to the columns in this example?
Each column, so the question was, what is the significance of the columns in this example? Each column basically says that in the received vector that I have, what is the contribution of this particular pixel? So just like in the gold code setting, we get to create the signatures, we create the gold codes. Here we create the columns. So there's not any significance per se. They're not signatures in that sense, but you can think of them as signatures of the pixels. Whoa. Okay. What do you see happening as time is going on? It's taking more and more time to do one iteration, right? Why is that happening? Our S matrix keeps getting bigger and bigger, right? So you have to do bigger and bigger matrix inversions every time to figure it out. Like if you were to do this with 10,000 measurements, you would have to invert a 10,000 by 10,000 matrix, right? Which would be a pretty big matrix to invert. You typically don't want to be in a situation where you're inverting that. Almost there. It's going to take some time. So it turns out that, as you can see, OMP is a pretty slow algorithm because it has these matrix inversions that are embedded into it, right? There are actually ways to speed up OMP using a procedure called Gram-Schmidt, which basically orthogonalizes your components, your signatures, explicitly. Right now we have almost orthogonal signatures. What it does is it explicitly orthogonalizes them, and therefore you can actually speed up your computation a lot. Again, we will not be covering Gram-Schmidt in this class right now, but you will learn it in 16B. So for those of you who want the extra penny, you can collect it for that now. We're almost there. So what is the sparsity level, right? We know how many iterations do we expect it to go for. We know that the sparsity is 960, so it's going to keep going until it gets 960 pixels. But you can start to see what the image really is, right? Okay, so we'll let that keep going in the background, and I'm going to move to the next part of the lecture, which is validation, which is finally coming to the question that you have all been asking me throughout the 3 lectures that we've been talking about OMP, right? You've been saying, well, but how do I decide when to stop? How do I decide when to stop? Here you're telling me that you know the sparsity level, but maybe I don't know the sparsity level. Maybe I don't know how many pixels there are. Maybe I don't know how many devices are transmitting. And to understand this, I want to introduce this concept of validation, which is basically one of the most fundamental concepts that's used many, many times over in in development of every single machine learning algorithm that is used. We're definitely not going to go into a full development of validation in the class this time because, there's multiple levels that we can go into, but I want to really just introduce you to the topic so that when you go into operator vision classes, you'll have a sense for what this is. And for this, I want to go back to the devices example. Okay, so we have these different devices that are transmitting, and we're saying that, well, I picked out one device, I picked out a second device, I picked out a third device. How do I know when to stop, right? And so let's think about, one way of doing this. Let's say I have my signatures that I've made, my gold codes, SA, SB, SC, so on and so forth, right? These correspond to my devices that I know. But what I can do is, in addition, I can make a set of ghost signatures. Maybe I'll call them GA, GB, GC, and so on. These are the different ghost signatures that you have. Is this still running? Okay. These are the different ghost signatures that you have, and you can say, well, I'm not going to use every single gold code that I have for a device. I'm going to keep some of my gold codes in reserve, and I'm never going to assign them to any device. So I know that these are gold codes that are valid gold codes, but they're not ever assigned to any device. So then what I could do potentially is I can say, well, let me keep picking off one device at a time, one signature at a time. As soon as I encounter a device, a signature, that belongs to my ghost set, my fake signature set that I have created, then I know that, hey, actually, this cannot be, this has to be some artifact of the noise. This cannot actually be because of a real device, right? So how do I know when to stop? As soon as I pick out a device from my fake ghost set. Right? This is something that we could do. And then we would know that basically the big thing, the reason that we're seeing this has to be some artifact of the noise, right? Like, I got a lot of questions in office hours as saying, well, how do you know if your OMP is actually working or not, right? You run this procedure, you get something out. How do you have any idea what you're getting is any good, right? Maybe you just got complete and utter and total garbage. How do you know whether this is at all valid? And this is one way that you can engineer into the system a level of redundancy that says, well, if you're picking out these ghost signals, you must just be picking out the noise. Because I know that no such device is actually transmitting. Right? That's great. But then what if, we have some enterprising Berkeley student who decides to build a device and looks at the list of signatures that are taken. They don't want to accidentally, impinge on some kind of IP or take a signature that is already taken. So they pick a ghost device and they actually build their device, and this device starts transmitting. Right? Maybe the ghost device that you're seeing is because someone decided to build that device. And it's actually there. How would you know if the ghost signature that you're detecting is actually a ghost signature and it's actually present? You just, made a mistake, or you're just detecting the noise. How could you potentially try and get around that kind of situation? Any ideas? Any thoughts? Yeah? Have the FCC reserve free gold codes. Absolutely a great idea, which is usually done. But people sometimes make illegal devices. And if you want to test your algorithm, we want to really try and do this. But in many cases, that will exactly work. Sometimes you don't have that much control. But other ideas potentially on what we could do? Yeah? Yeah, can you somehow validate that what you're seeing? The idea is saying, can you somehow validate what you're actually getting, right? You're saying like, well, if I am getting this, signature, is it actually that some student made some device? Or is it that there's some, I'm just detecting the noise? So, what one would want to do, what a good engineer would do, is you would collect a validation set. You would say, I have my received signal R, and maybe my received signal R is coming from microphone 1, or it's coming from my device, my first home box, right? But if I have, say, a second microphone, a second receiver, where I can collect basically an independent measurement of the same devices. So these are two devices. Now they're both placed in the same room, but maybe at slightly different locations. So this second device, the noise that is coming into this device is different from the noise that is coming into this device. So if there's truly a device that is present, both of them should pick it up. But if I see a ghost device that's present only in one signal and not in the second signal, then I can say, well, you must actually be noise, right? This ghost device is just an artifact of noise. So I have basically an R1, or R primary, and R validation. And I say basically the strongest signals plus devices will be present in both. And as soon as you end up in a situation where the OMP running on the two different signals starts giving you different devices that are present, you can say, hey, come on guys, you're in the same room at essentially the same location. You're just making up stuff by reading the noise, right? That's basically your way of saying that, okay, there's something going wrong here. This is the idea of validation in machine learning. And this is an idea that, you have to grapple with a lot in machine learning. Could I get back both the document cameras? So in general, in machine learning, you will always have to ask the question, how do I know if my model is any good, right? I can make a model. I can make a model, for example, to predict the stock prices, right? And I can make whatever model I wanted. But how do I know that I actually want to use it, right? I could make a model to, predict whether people are going to like a certain shirt or like a certain design. I think someone posted an extra credit submission on Piazza about this. How do I actually know, whether my model is any good? Let's say I'm modeling not the stock, but I'm building a circuit. I'm trying to understand, how a certain component is behaving. I'm trying to just fit a polynomial to some data. How do I know if what I'm doing is any good? Like, say I have some data, right? I can fit a polynomial to it. I can say, let's say this is my y, this is my x. I can say y is equal to alpha 1x plus alpha naught. This is one model. Model 1. Model 2 is y is equal to alpha 2x squared plus alpha 1x plus alpha naught. Model 3 is y is equal to alpha 3x cubed plus alpha 2x squared plus alpha 1x plus alpha naught. Right? I can make as many models as I want. And I can take whatever model I want, and I could fit it to whatever data I want. But I need to know that I'm not just making up nonsense, right? And this is basically the idea of validation. So if I could go back to my computer for a minute. Perfect. So this is some code that might be familiar to you for those of you who have already started the homework. But let's say you are given actually a device, right? Let's say you're trying to understand the IV curve for a certain device, or you're trying to understand, the relationship between x and y variables, and you're given this data. It looks awfully, line-like, but how do I know what I can fit it with, right? So here I have some code that I can basically input the degree of a polynomial that I want to fit, and it'll fit it for me. So I could fit a polynomial of degree 1, and you can see that it's plotting a line. I could try and fit a polynomial of degree 2. I can try and fit a polynomial of degree 3. And pay attention to this number that is the error magnitude here, right? This is basically capturing how many points are not on the line. So I can pick degree 4. So it's 50.8. I can pick degree 5. My error decreased a little bit. I can pick degree 6. My error decreased even a little bit more. As I keep increasing the degree of this polynomial, my error keeps going more and more, keeps going down, right? I'm increasing the complexity of my polynomial and increasing the complexity of my model, and basically then saying that, well, I can improve things. But how do I know I'm not just fitting the noise, right? How do I know that this is not just coming from something made up? So for this, what you can do is basically, what you do is you take the data that you have and you divide it up into two sets. You divide it up into a training data set, and you divide it up into a validation data set. And you say, well, I'm going to see and fit a model to the half of the data points, or some third of the data points. That is basically what are the data points that I have. And then I take some remaining part of the data points that I don't use for this training purpose. I don't use them to fit my least squares coefficients. And I evaluate the performance on these other data points. Do you see that I've basically split my data into these two parts? So what this plot here is showing is that I can start at a degree 1 polynomial, I can end at a degree 15 polynomial, and as I keep increasing the degree, I keep somehow, fitting all the noise points, and this error, which is just saying that, well, how far away are each of my points from the line, just keeps getting better and better, because the line the more degree I have, it keeps wiggling to fit more and more points. But we know that that's somehow not a good thing. So what we're going to do is instead, we're going to fit the polynomial on these training points, and we're going to compute the error, we're going to compute the cost on these validation data points. And so what this validation cost is saying, you've trained on these guys, this training data, but now I'm going to test you on this validation data. And now, if I look at my cost, well, it keeps starting to go up. Basically, I can say that, well, you fitted the particular noise that was in your training data, you fit. And you decreased your cost there. But in a more general case, you're actually going to do quite poorly. So that's just a 1 degree example, but you can also think about, let's say you have this, right? This is the data that you're given, you want to try and fit a polynomial and understand what's going on. So let's say I can choose by starting to fit a degree 1, right? Doesn't look too good. I can fit degree 2. Doesn't look too good. Degree 3, making progress. Degree 4, better. Degree 5, how do I know when to stop? I can do degree 10. Whoa, they're all good, right? Which one do I pick? This is where I basically need to now look at this validation cost, right? I take this data and I say, well, I'm actually going to split it. I'm going to say some of it is training data, where I can use to choose my model. The rest is validation data. And now I see a massive cost at degree 1, massive cost at degree 2. At degree 3, suddenly the cost drops. And it looks like it's flatlining here. But actually, that's just because this axis is skewed. So if I actually start at degree 3, you can see that degree 4, degree 5, degree 6, actually the cost is increasing. So what I want to just communicate to you is that whenever you're doing this engineering job, right, you're saying, well, let me model the world as X. Let me model the world as Y. Let me have this setup. Make sure you actually validate your models. Divide your data up into training data and validation data. It's easy to make a model that works, but you have no way of knowing whether it's good or not. You can run OMP on anything, but you might violate the sparsity assumptions, right? How do you know that you're not just picking out noise? This is where validation comes in, and it's an important tool of any engineer and anyone who wants to, do any kind of data processing going forward. So I'm going to basically end the lecture here. Don't have too much time because there's HCAN people who want to go and talk about surveys, but just to remind all of you of where you've come so far, right? You have just been introduced to validation, which is a key concept that basically everyone in machine learning and any kind of engineer uses all the time. But if you think about where you've come so far, right? Where did you start off at the beginning of the semester? You started off with just deciding how to learn to model. And what you have is, well, you've built your own camera, you've built 2 different types of touchscreens, and you've built your own GPS. If you think about it, that's a pretty impressive accomplishment for about 3 months of time. So make sure you don't forget that, and make sure you're proud of how far you've come this semester. And this wasn't the only class you were taking. You did this while taking a series of other classes, and for many of you, navigating your first semester at Berkeley. So make sure that you remember that, enjoy it, and there's a lot of other courses that you can go forward to take. So hopefully this will inspire you to, explore a large variety of classes. And if any of you have any questions about any of these classes, Professor Boser and I are always very, very happy to talk about it. So look forward to seeing some of you on course staff next semester, and I will pass on to HKN. I'll be outside at the end of class if anyone has any questions, but for HKN, I'm required to leave the room. Thank you. I'll get out. Yeah. Oh, you want to use the...
I think you need a projector.
If you have a minute, we would really appreciate if you could stay for the HKN reviews. This is really important for us as course staff to understand how things went over the course of the semester. It's just 5 minutes, but these are your fellow students. They're putting in time to be here and do this service for the department. It would be really nice if you could just wait for 5 more minutes. Thank you so much.
Thank you. Okay. Yeah. Hi, everyone. So we're from HKN. As Professor Ranade said, we're just here to encourage you all to do the course evaluations. They're super important for the professors and all the TAs to understand how they did. And your feedback will be read by them and will be taken into account for future iterations of the class. So basically, here's the link. It's just course-evaluations.berkeley.edu. And then these are also good practices for when you're doing it. You also probably got emails about doing course evaluations, so hopefully a lot of you have done it already. But in case you haven't, here's 5 or 6 minutes to do it right now. Thank you.
Yeah, so these course evaluations are really, really important. The only reason why the class is how it is right now is because all the previous years, every single year, the students have done these course evaluations. So if you really enjoyed this class, it'd be a good time to sort of voice your opinion and say what you liked about it so it can continue staying good. And if you didn't like it so much, then this is a perfect opportunity for you to say what part of the class you thought did not go as well so it can be changed and improved for all the future years of people doing this. So please, again, if you haven't done your course evaluations, please go up to course-evaluations.berkeley.edu right now. We're giving you time right now in class to do this. It'll take just a few 5 to 10 minutes and it'll really help out. Thank you. to 12. I don't think we can reach 12. But 12 would just say thanks for coming.
Yeah, I got like my candidate challenge. Instead of like questions, it was like like present during June 3.
Oh, okay.
And I was like, wanted to do it like the day of, but then I got like maybe somebody else was like, hey, there's like Indian mob tiger or whatever. And I was like,
Oh, I saw that.
I replied to that. Right.
You're just like, I'm doing that right now.
So doing that.
My original awkward challenge was supposed to be like, at VM3, like, pick up a notebook and like, oh no, sorry. At VM3, he was like, oh, I'm gonna stand up and like, when Frank and start saying stuff about it, and I need you to
Yeah.
like get down. I was like, okay, that's like really good. But then the day after, like, oh, by the way, you're gonna be standing up and you're gonna start like saying all this like stupid stuff, right? So then I was just like, oh wait, and I was like, I don't know, yeah, I just felt a bit weird about it, and so it's like a random like auto presentation. Oh, I was like, whatever.
I did get that done.
I feel like some of the challenges were like a lot easier to do.
Yeah, definitely. Some of the rough time was easy.
I mean,
walked over, took a picture, and then
oh wow. Is it interrupt?
yeah, it was kind of far. It was kind of far. It was a little bit walking, but like, it wasn't that far.
One more minute. I made it. Did we just leave everything here?
I think so. The rest of it is just for lecture and classes. It's not weird to follow this.
I guess we can just tell her when we leave. Oh, she said she's outside.
Oh yeah.
Part of a long night was so like, yeah, just like wait there with them and walk out.
I went to CS Labs and tried to get checked off.
Oh,
It was
really?
too long,
Oh,
so I was like,
what part?
687.
Not 12 or 14? I haven't done 14.
It's on like Maverick. I think I got it, but I'm not sure.
Did you get checked off for the week?
Well, you said there would be a couple check offs.
I think I went because I was out for like so long.
I might just do it now.
Are you 170?
No.
Okay.
70.
Oh,
It's 2.
okay.
Okay, it's 2, so yeah, y'all are good to go. If you have any questions.
Yeah, if you have any questions, you can just, I guess we'll hang out for a bit, but like you don't have to say anymore. If you're still doing a course evals, that'd be great. But thanks. Oh, what's up, Michael? This is 16A.